My name is Lucas Botero, and this summer I worked on the 3D printing with robot arm and defect correction, guided by Professor Shen Feng, PhD candidate Su Chu, and I worked alongside Master candidate Shin-Soo Yang. 3D printing has evolved a lot during the past years. New materials can be printed, such as plastics, composites, and even metal. Printing methods have also been developed further, and Figure 1 shows a list of them. The most common one being material extrusion, where the material is extruded layer by layer and they dry before the next layer is applied. I've highlighted material jetting because it's the one this project focuses on. It's similar to material extrusion, but the layers don't get to dry before the next one is applied. All of these methods suffer from the same problem, printing volume. As you can see, the printer has to be greater in size than the printing volume. Another problem are defects very common in material jetting. You can see here the filament tearing and the filament splitting, creating gaps which affect the structural rigidity of the object being printed. Our solution: we are using an industrial robot arm called the UR10E, which has great reach while still having a small form factor. Its 6 degrees of freedom allow it for great flexibility, and it has a high precision. So we're using the UR10E, a clay tank, a pneumatic air compressor, a printing head, and to control it, an Arduino board and a micro-step driver. The material we'll print is clay. Here is the experimental setup, and we're using the air compressor, which pushes air inside the clay tank, which then pushes the clay into the printing head, and the robot places it precisely. We use this 3D printed mount to attach the printing head to the robot. The programming was tough, and we had to set each waypoint for the printing path. Milestone 1 was a square outline, and you can see here we still have some defects. Milestone 2 was a solid cube, which you can see printing on the left, and the results are shown on the right. Milestone 3 was a 40% infill cube. You can see we printed 3 cubes, and they each have different outcomes. The best cube we printed was this one shown on the right. You can see a top surface, and on the right you can see we broke the cube to show the internal structure. Here is the printing process for the 40% infill cube. Next, we implemented defect detection by using an RGBD camera, which creates a point cloud. This basically means that each point has an associated X, Y, and Z coordinate. Then we can compare this to a CAD model, and the differences are also known as defects. This is the point cloud we created. You can see it's very accurate because here the cube was measured to be 59 millimeters, and in reality it measured 59.2. Future work for this project includes implementing a program that can correct the defects in real time. We will use machine learning to set the ideal combination between the variables, which are the UR10 speed, the printing head speed, the air pressure, and the printing head nozzle position. The potential for this project is huge. It can be used in all types of 3D printing, especially in houses, where we want to assure the highest structural rigidity by having no defects. Thank you.